So looking at problem 13 on yours, you have this law of multiple proportions, and we're going to look at an illustration for illustrating the law of multiple proportions. So we're given the following data set that were collected for several compounds of nitrogen and oxygen. So we are going to assume that in every one of the compounds we only have 1 gram of oxygen, and these are the relative amounts of nitrogen. So let's do this. Oxygen will be in blue, and nitrogen will write in green. So just kind of starting off here, what do you notice is the difference between this number and that number? All right, so cut in half, or if we're going this direction, how do we get to there? We double it. So going from B to A, what do? Double it again. If we go from C to A, it's going to be quadrupled. All right, so really when we're looking at this, we're just going to pick any one of these compounds and assume that the nitrogen to oxygen is 1 to 1 here. So if we pick compound B, and we're going to say that compound B is NO. So we have that's what compound B looks like. If compound B is 1 to 1, what would compound C be? We have to have half as many oxygens, so or half as many nitrogens. So we can't have a half of a nitrogen. So what do we have to do to oxygen? Double it. So this one is going to be. It didn't change. Come on. So it'd be NO2, right? Did I do that right? For compound C? All right. So what would compound A be? Which one? Yeah. So how would I write, I guess the question I'm asking, how would I write compound A? You have half as many, you have twice as many nitrogens. And so the relative proportion is going to stay the same. Oxygen isn't changing, so it's going to be N2O. So based off of this information, we get 3 different sets on there. If you look down further at the drawings that we have down here, the one that we just did was this one. So based on the information that we had, if we said that B was the 1-to-1 relationship, that means that A is going to have 2 to 1, and C is going to have 1 to 2. And that's exactly what we got, because we got NO2, NO, and N2O. Now the next way, you could have just started setting A as 1 to 1, and then you'd have had this one as NO, but then you end up with NO2 or NO4, like that. So you end up with a different combination. And then if you set the last one and this one, don't even, that one's not even one I'd want you to even try. What they did was set B as a 2-to-2 ratio, and then it just gets larger from there. So you wouldn't have any reason to do that one. Talking about review, what do we already know? We already know a lot of things about the periodic table. What do we call the elements along that line? Metalloids. All right. Actually, I'll just do this. I don't have it on there. All right. What about this column right here? Alkali. This column, alkaline. These are transition. These are intertransition. And they kind of fit right there. Or actually, sorry, I drew my lines in the wrong place. They should actually go. They should go there. All right. So what I really want you to do with the periodic table for right now, be familiar with what you know. Know the names of the families, know the names of the regions, things like that. I'm not going to ask you to know every element on here. That's not something I ever want anybody to do. But as you use it more and more, there will be elements that you get more and more familiar with. All right. So this number right here, this 39, what is that number? It's atomic number. The numbers that usually appear down here that are some sort of, it's the atomic mass, but specifically when it's a decimal, it's the average atomic mass. It's an average of all of the, guys, the average atomic mass is an average of all of the what? So the element. Close, you start with an I. Isotopes. So just be familiar with those type of things. Remember that this decimal number doesn't specifically tell us the number of neutrons. You can solve for it, but that's an average, so you have to have a specific isotope to get the real number of neutrons and things like that. So looking a little bit further down, does anybody remember what we call that arrangement of writing an element out like that? Isotope notation. You're going to see this way a lot in this class. What I want you to do right now with this one is go ahead, make a column for protons, neutrons, and electrons. We're going to go ahead and do some real quick math. Right here, we're on page 11. So this one's pretty straightforward. So how many protons in this isotope of gold? 47. Do we see a charge listed with this isotope? No. So how many electrons is it going to be? 47. When there is no charge, protons and electrons are exactly the same. How many neutrons will there be? Or 62. 109 minus 47 gives us 62. All right, looking at, and we're going to add an E as well, but I'll tell you what that one is in a minute. All right, so looking at this one, how many protons? How many neutrons? How many electrons? 12. That one just worked out that they're all the same. All right, again, 24 minus 12 is 12. All right, so for aluminum, protons, 13, 11, and 13. All right, let me scroll down a little bit further. All right, so for E, I want to do this one. We have 14 over 7, neutron, nitrogen, and it's a minus 3. So it's going to be symbol for nitrogen. It's a mass of 14, atomic number of 7, and this one is a negative 3. So just identifying a couple of things. What do we call positive ions? Cations, not cations. And then what do we call a negative ion? Anion, not anion. All right. So let's go ahead, just recall how many protons? We're looking at D. 47. How many neutrons? 60. 107 minus 47 is 60. And then how many protons? Electrons? 46. Why 46? We have one less. We have a plus 1 charge, so we have one less there. All right. Going through this one, how many protons? 7. How many? 7. And then 10 because we have a negative 3 charge, so we have 3 extra electrons. All right. I don't know if Ms. Deloche makes you memorize these or goes into this detail on it. I don't. This is one of the things that I just kind of skip over in Chem 1. So now you have to memorize something. I think usually we just had you fill out certain ones on the periodic table. We didn't go into a great detail on them. So I'm just going to quickly go through these. So charges of common univalent cations. If it's univalent, that means it has how many charges? 1. So univalent cations and anions, the ones that we remember, if it's in group 1, what's the common charge of group 1? Plus 1. Group 2? Is a plus 2. Now, I'm going to say group 3A, but there's really only one element that technically counts in group 3A. Does anybody know what element that is that's going to produce this? Not boron. Boron's considered a nonmetal or a metalloid. Aluminum. So, group... I do. Can you send to Ms. Hall a minute, please? Sure. This is Ms. Hall. That's the very front one by where the old band room was. All right. So group 3A, and it's really only one I'm talking about here is aluminum, has a plus 3. That's ones that you knew already. I'm going to leave carbon, group 4A, off because there's funny stuff going on there, whether it's positive, negative, all of that. The way that we've taught you in the past, yeah, it's kind of both. It goes both ways, but more so than anything, carbon and silicon form covalent bonds so they don't ionize. Germanium, tin, and lead are some special cases, and we'll see that in just a minute. All right, so we'll go ahead and do the nitrogen group. What's the normal charge for a nitrogen group? -3. Y'all remember that. What's the normal charge for oxygen group? minus 2. Sorry for my handwriting. And the normal charge of the halogens. Minus 1. All right, noble gases do not form ions, and if they ever do bond, they form covalent bonds. So they're not part of this. Now, these are the ones that you may have known them, or you may not. Actually, let's do these first. All right, so look at the periodic table, and you see this little zigzag starting with aluminum, and then you have zinc, and then you have silver. Aluminum, zinc, and silver are all univalent. Aluminum is +3. We already talked about that. Zinc is going to be, it's one step over, so it's a +2. And silver is +1. All right. Now notice that cadmium is on the same line as zinc. So what do you expect cadmium's charge to be? +2. All right, so those are your common univalent charges, or common univalent cations and anions. All right, multivalents are a little bit easier, but it's easy just to show them in groupings. So looking at the periodic table, you see how group 8 there, or I guess it's 8B, it kind of goes over 3 columns, iron, nickel, and cobalt. So iron, nickel, and cobalt, they have a +2, +3 charge. All right, I'm still getting used to this board. The other one that we have is copper. And mercury. Copper and mercury can be +1, +2. All right. Now, this is special about mercury. Whenever mercury is a +1 charge, we write it like this. When mercury is a +1 charge, it's diatomic. So you would write it as Hg2 with a +2 charge. You won't see mercury. You won't ever see Hg +1. You would see diatomic mercury with a +2 charge, and what that's telling us is each one of those mercuries have a +1. All right. So that one's kind of a odd partnering. All right. We have gold has multivalent. Does anybody know the valences of gold? +1, +3. That's not D. This should be a B, right? Tin and lead is +2, +4, and then is that antimony? Antimony and bismuth is a +3, +5. All right. The only other one that I would add there is arsenic. When arsenic is normally a metalloid, when arsenic acts like a metal, so sometimes arsenic will act like a metal, it has a +3, +5 also. Yes, sir. That should be a +2, +3. That first thing was supposed to be an arrow. I'm still trying to get used to the board a little bit. Both iron, nickel, and cobalt are all +2, +3. So they're a group together. Each one of these is all multivalent. They all have multiple things. All right. Does the metal form more than one cation? So if it has more than one valence, like the list that we just went through, then if it does, you need to use the Roman numerals. Use Roman numeral to name it, so you would have something like copper 1 sulfate, something like that. Except for we're not doing sulfate, so it'd be like copper 1 oxide or something to that extent, copper 2 oxide. And then if it does not have form more than one, if it's one of those standard ones like lithium, sodium, potassium, we just name what's there, name it for the cation. All right, so, and then if it's going on this other side, if no metal is present, what type of bond is it? Covalent. And what's special about naming covalents? What do we use? Use prefixes. All right, so I'm not going to do, I'm not going to do all of these. I'm just going to take a couple of them. So this first set, 11, these are all ionic. So how would we name NaCl? Sodium. All right, so who can tell me what I did wrong on there? What did I do incorrectly? Capitalize the C. Should just be a lowercase c. All right, next one. Our potassium sulfate, sulfide. All right, I'm going to skip down. Make sure. Yes. Let's do cobalt was multivalent, right? Had more than one charge. So how do we find out what charge of cobalt we're dealing with here? Do it based off the second element. What is the normal charge of iodine? -1. So if it takes 3 iodines to go with cobalt, what's cobalt's charge this time? +3. So cobalt's a +3, iodine's a -1, so that means it is going to be cobalt 3 iodide. Does that make sense? And we'll do one other one because I want to do it with this one. We have Cu3N2. Again, we have to look at the normal charge of nitrogen because that one is univalent. It only has one charge. Nitrogen's a -2. So if it takes 2 of those to respond with 3 of those, so that's going to give us a -4 overall, and this will give us, to counteract the -4, nitrogen is -3. That was sorry. Thank you for catching that. All right, so nitrogen, that's giving us a -6 overall. It takes 3 of that, so that means that this one has to be a +2. So it's going to be copper 2 copper 2 nitride. All right. Yeah, you only have to use the Roman numerals when you're writing it out. Yeah, but that you can't always rely on that on multivalent because remember we reduce. Um, so, um, so if we reduce, sometimes it doesn't come out that way. All right, moving on. All right, looking at number 12. All right, number 12 is more ionics. It's just going the opposite way. So calcium sulfide. What we just have to look up their common charges. What's calcium's normal charge? +2. Sulfur is normally a -2. So what is our formula going to be on this one? CAS. Let's look at this one with the Roman numeral. Bismuth 5 sulfate. What's the charge of bismuth? +5. And then sulfur is normally -2. So it's going to be Vi2S5. All right. Nickel 3 bromide. That 3 is telling us that nickel is a +3, bromine's a -1. So it's going to be NiBr3. Do I need to do any more of those? All right. All right. What's different about number 13? They're all covalent. So I'm not going to do these. I'm going to stop kind of teaching right here, but let's do the, does anybody remember the prefixes? Mon. All right, it's tetra. Remember, we're not dealing. This one is chemistry, not algebra. I mean, not geometry. So it's going to be pent. Is it hex? And yeah. So it's that one is hex, and then it's helped. All right. So mon, di, tri, tetra, pent, hex, hept, oct, non, and dec, or deca. I'd have to look it up. I don't go beyond those. I probably won't ask you anything. I think. All right. And same thing down there. We're going to stop with binary. We'll pick up ternary and acids tomorrow. What I do want you to work on, I would like homework sheet 1A if you have it already, and I would like for you to work on 1B if you. Sure. Yes. 1B is up here. It's the one with the green on top and all of that. Roman's picking them up. Roman has them. Yeah. Not 1C. Not 1C yet. where you can start it, but it's not. We haven't covered all of it yet.